In designing my programming language, True, TRU, I realized, not realized, because having these thoughts for a while. It seems to me like there aren't really that many languages. I think Erlang might be, but even then, there aren't that many languages that like make async or concurrency easy. Like take Rust for example, which a lot of people hail to be the best async model or best concurrency model, or at least one of the best. I don't know, because like it's safe and all that, or it's supposed to be. People call Async Rust a whole other language inside Rust, which is like not what you want from a language you design. Like the language should be like Rust should be Rust, and like Rust has concurrency, you know, not like Async Rust is like this term that people use separately from normal Rust. Because concurrency is also very useful, you know, like if I'm making an application that just happens to have operations that can be computed in parallel, then yeah, like why not do that? It's just makes things faster. So I personally have not used concurrency like ever in all my projects, just because I just haven't gotten around to it. Like with C++, I know it exists, but like to use it isn't like particularly like natural, I guess. Like it's not like, oh, I have this operation, I'm not gonna make it concurrent. No, it's like I need to spawn threads, like manage threads, and make sure like I don't get data races, you know. Or like in Rust, like this whole async model, and in C#. Actually, I have used it in C# for Unity games with the async await, but like that forces me to like completely change how I structure my program, because now I have like, you know, it's like an infection. Like suddenly all my functions become async. And it's like, well, like what? Like I like writing C# with async await for Unity genuinely felt like I was using a different language as well. So when I'm making my language, I want it to feel more integrated, more like just the language just happens to not just happens to, but like it just supports concurrency in a natural way. So like you don't have, like, to the point where like you might not even have to think about it. Maybe the compiler could just do it for you in situations where it makes sense. But for that to happen, the compiler needs to know when things are parallel, and that's quite difficult apparently. Like with C++'s standard SIMD, apparently, while it's called SIMD, and for those who know, SIMD is single instruction multiple data or something. So like you process multiple data in one instruction. Like let's say I'm using a SIMD 256 buffer. That's 256 bits. That means it can fit 8 floats. So then I could add 8 floats to another 8 floats in one instruction, which is, you know, it's really fast because it's in one instruction. And you're effectively adding them in parallel. So like there's no multi-threading in this case or anything like that, because like or like no multi-core, because like it's one instruction on the CPU. But like it's the same idea, where if the compiler knew when it could do that, then it could just do that automatically for you and optimize things. But the downsides are, first of all, it's not always obvious when it can do that. Like I think the simplest case would be like a for loop, where I'm doing like let's say I have 2 arrays that are contiguous, because that also they also have to be contiguous. That's also a requirement, and then I add them together in a simple for loop. Like the compiler, I think, can optimize that into SIMD, but then there are other cases which are less obvious, and not to mention as well, it's not guaranteed, right? Like it's then at the what's the word? The mercy, or the discretion of the compiler to optimize that for you. So like you can't force SIMD if you don't use it explicitly, which is weird. Because like SIMD, like it's an instruction on computers. In the same way, like with multi-core, or just parallelism, like you know, like when you're writing the high level stuff, you don't really care how it's done in parallel. All you care about is that it's done in parallel, and that you don't get like data races. So like it's a very low level thing, like SIMD, concurrency, or like rather multi-threading and multi-core CPU stuff. Like that's all low level stuff that on the high level you don't really want to think about. You just want it to use it when it can, you know, which is weird. And also like as I was saying, standard SIMD in C++, although it's called SIMD, I've asked in the C++ Discord server, and apparently it's like while it's called that, you can also just like think about it or think of it as, like imagine if instead of it being called standard SIMD, it was called standard data that can be computed in parallel. It's like that, because like yes, it applies to SIMD, but like the same idea of having that kind of type also applies to if I want to do things for multi-core or multi-thread. All it says is that I can add these, or like, well, I can operate on this data at once, you know, like in one instruction is the idea. But like that one instruction means like concurrently without them conflicting, or like without issues like coming of it. Now that's not entirely true because SIMD also is SIMD. So like again, like it has to be a contiguous array, whereas like with multi-threading or multi-core, because multi-threading, while it is technically in parallel, multi-core is like truly in parallel, right? But still, like data races, whatever. I think that's the same. But like those don't have to be on contiguous data. It could be something else, like having different, I don't know, like different tabs in your browser would probably operate on different threads, and possibly on different cores, right? So then you have like multiple things happening at once. So like the idea of multiple things happening at once, that can be thought of in like a high level. Like I have multiple tabs I want to be running at the same time. Like I can do that. So maybe there's something there, but like just generally, you don't. All you care is that it's done concurrently, and then you kind of want the low level implementation to handle like how that works behind the scenes. And my issue so far with concurrency in languages is that the concurrency ripples to the highest level. Like if I have something that's async, it's really hard to wrap it and hide it, and that's why I tried doing with C#, and because I wanted like the async to work with the rest of my non-async project, but then I realized like yeah, I can't do this. Like it's infectious. I have to just make everything more or less async await to use it, because otherwise like I can't really encapsulate it in a way that's nice. Or you know, maybe I can. But like from my limited experience, I wasn't able to find a way that works for me, or that works, I guess, full stop, to have it be hidden. So it's interesting. That's something because like I feel like to tackle that issue, like it needs to be a fundamental programming language thing, like level design thing, and I feel like it comes from mixing expression-based programming with or expression-oriented programming with not object-oriented programming, procedural programming. Because expressions are inherently, I mean, they're not really parallel, but like the idea is that they happen on like the same step, kind of. Like if I want to add 5 plus 2, like I can just add 7, you know, and like that's like one motion kind of. It's hard to explain. But my point is, I feel like functional programming is in a better position, minus lazy evaluation, because that causes issues with threading, with concurrency. But minus lazy evaluation, it seems like functional programming is in a much better place to have compilers be able to optimize for concurrency automatically, just because they don't have to worry about like side effects. Because side effects is like kind of the thing that breaks concurrency a lot of the time, or at least makes it harder for compilers to reason about concurrency. Whereas procedural languages like C++, Rust to an extent, although Rust is technically quite functional. I believe the AST, like the abstract syntax tree for Rust, is functional, or like is expression null. It's kind of hard to explain that without getting into the nitty gritty. Not that I've even looked deep into it myself, but yeah. Point is, procedural programming, while it feels natural, you know, to say do this and do this and do this, we don't really have a good way to express do these together and then do this and then do this, or like spawn these and then like check back on them later, all while making sure there are no data races. That's really interesting. Like you want a language that lets you still do, you know, this then do this then do this, because that's, you know, that's kind of a given. You need to have some kind of procedural code, because tasks are inherently procedural, right? You do this, and then you're probably going to want to do something else afterwards, after the thing is finished. but hold on. But then you also want a way to express these can happen at the same time, or have these start now and check back on them later. I guess those are like two different things. Standard CMD kind of tackles the former, where it's like these it tells the compiler these can be done at the same time, so use CMD on them. And maybe there's some other constructs that can also be done for like multi-core maybe, but I'm not sure. And then the second one is more like start this and then check back on that thread later through like an interrupt. But then make sure that when I receive that interrupt that says, yo, I've finished my task, you can now continue with what you wanted to do here, it needs to be in such a way that you don't get data races. Like if I'm in the middle of doing something, keep in mind the CPU needs to be able to switch, right, between different things. And like if I mess up the state, because like let's say what's like a good example? Let's say I have a hand that is moving objects around, right? And I put in a request at the baker's to get some bread. And then I say, okay, tell me when you're done and I'll come fetch it. And then, yeah, until then, I'm gonna move these oranges from this basket to this basket. So then I'm moving the oranges, and then here I take an orange, I pick it up, I start moving it towards the other basket. Oh, but suddenly, the baker has arrived with the bread. And he's interrupted me and said, yo, I'm done. So now I stop what I'm doing, right, with the orange in my hand. I go to the baker's. He's like, why is there an orange in your hand? I'm like, yeah, whatever, just scrap that. Whatever, drop it. Take the bread, do that thing, go back to my orange task. What's happened? That orange that I was moving has now just been lost. Right? Like, that's the kind of thing that could happen with data races. So then you need some kind of way to say, okay, if you notify me while I'm moving an orange, I'm going to wait until I finish moving that orange, because that's a task that could lead to data corruption, right? Imagine that. Now, there are ways to do that, and like there are models for that, but I feel like the way the low-level implementation of that is very interesting. I mean, if you're interested in operating systems, that goes really deep into that, because operating systems have to handle, different processes every millisecond, or a few milliseconds, whatever. Like, there's a lot of task switching going on, which could also be supported by multi-core. But then even on like the high level, the way, like, it's just, I don't know. Point is, it's very interesting, and I really should get into using concurrency myself, so that I can have a better, well, just be better informed on what works and what is kind of leaves a lot to be desired. Which is why I am going to be watching this video today, Async Rust, explained in 20 minutes, just to kind of get an idea of Async Rust, because I've not used Async Rust ever. And I'm very curious to see how it works. Of course, I could use Async Rust myself, and like that would also teach me. But I don't really have any projects in mind right now. I'll get around to it eventually, but for now, this will be like a soft introduction to kind of get my brain going and like start triggering ideas. So let's watch that.
Async Rust will break your brain. In other languages like Go, Java.
See, that's not a good start, It will break your brain. Like, I get it's hard, especially for like people who are less experienced programmers, I guess. Just like generally speaking, I don't understand much about memory management, but like, it shouldn't be that much hard. Well, yeah, we would prefer for it to not be that hard, right?
JavaScript or C#, async code just works. But in Rust, a similar code snippet won't even run.
What's that mean, just works? Like, are there any issues with how Go and JavaScript and all that work? Like, I know JavaScript uses futures, I think, and Go has like its Go. Are they called Go routines? Like coroutines, but Go routines, I think, or something like that.
Why?
I've not used
Because
Go
Rust's async model is fundamentally different. Async Rust is more powerful,
But note as well, Go and JavaScript are garbage collected, or like they have a runtime, whereas Rust does not have a runtime. So I'm wondering, like, can you have async without a runtime? Like, yeah, like I guess you need some kind of like thread manager, or like, but like, can you not just like work with the OS directly? I think you can use primitives, but then like if I can use primitives, why can I not just rely on that? I think there are many different use cases for concurrency. or like many different forms of concurrency, and that's why even within Rust, like you can use async Rust for concurrency, but you don't have to. You can also use like standard thread and do that, or you can use like Tokyo. So that I also understand, but like I'm not familiar with the different use cases then.
Perform it, but also a lot more confusing if you expect it to work like other languages. In this video, we'll cover the 3 areas of async Rust that trip up even senior developers. By the end of this video, you'll build the intuition to start writing production-grade async Rust with confidence. Let's start with the first set of concepts. Exciting news, this video is part of the official launch series for the Rust Live Accelerator, opening this June. More on that later.
What?
In Rust, calling an async function doesn't actually execute the async function. If you're coming from JavaScript
So it's lazy, okay.
or Go, this is genuinely confusing. In those languages, calling an async function starts something. Work begins. In Rust, it doesn't. And that's not a bug, that's a design decision. When you call an async function in Rust, you get back a future. A future is just data. A description of...
Other features were in JavaScript too, no? Or am I thinking of promises? But I thought JavaScript had both features and promises. Maybe it's like a thing you can choose between. I mean, I'm sure JavaScript is like full of many different options because of how, you know, NPM packages and all that.
work to be completed. Futures are similar to promises in JavaScript, but with one key difference.
Does JavaScript use function as a keyword? Instead of FN?
In JavaScript, a promise is eager. The moment you create it, it starts executing.
Right.
In Rust, futures are lazy. They won't start executing unless explicitly told to do so. This design decision allows developers to have full control over when and where async work starts. That means Rust never does work you didn't ask for.
But can't you just do that by calling the function and then you choose where it works?
This matters a lot when you're building systems that require high performance and throughput. So how do you actually make a future run? You turn it into a task. Tasks are futures that have been handed off to an async runtime for execution. So to make this into working async Rust code, we first have to introduce an async runtime. We'll use
an async runtime. So there's a runtime. I've used tasks in C#, but I don't know if they're the same or not.
Use Tokyo, the most popular async runtime in Rust. You configure it with a single act.
I watched a video by No Boilerplate where he talks about async, and apparently Tokyo requires you to use static lifetimes, which removes borrow checking, which is not ideal.
Attribute above your main function. And then you add async to the front of your main function. Finally, to turn a future into a task, you wrap it in Tokyo spawn. The moment you do that, the future is handed off to the Tokyo runtime.
I don't know why it has to be Tokyo, because Tokyo is just a library, right? Like, it's not like part of the language. So, what does Tokyo do under the hood that I can't just do myself?
Task is now scheduled for execution on the Tokyo async runtime. But what exactly is an async runtime? An async runtime is a system that manages the execution of async work. Think of the async runtime like a manager. It decides which tasks get worked on, in which order, and on which threads.
Okay. Yeah. So, I mean, yeah, it's not inherently bad, right? But, like, it is like a subsystem. But, I mean, every app will have subsystems of some sort, right? Why is it called a runtime? Because, like, when I think of like a runtime, I think of like a garbage collector being a runtime, or like the Go runtime. But maybe that refers to concurrency specifically. I don't know.
Without it, your futures just sit there forever. In JavaScript, C# and Go, the async runtime is built into the language.
Yeah.
In Rust, the async runtime is explicitly not built into the language.
Yeah.
This is another intentional design decision. By letting the Rust community create async runtimes as third-party libraries, Rust is not locked into using one specific runtime. This allows developers to decide which runtime makes the most sense for their use case.
Or even to just not use runtime at all, I guess. But it is cool how you can do that. Like I have wondered, like, could you create a garbage collection subsystem within Rust? Or like, yeah, like, could you make your own garbage collector in Rust and use that if you want to, or would that be like incompatible with how it manages memory? I mean, like that's like the main use case I can think of, or even like code your own. I mean, I guess you could, right? Like if you can code your own garbage collected language in Rust, then surely you can also use that garbage collection strategy in Rust as well. We're probably using some like special user defined types or something like that. Same way that you could have like JavaScript style type system where you can like reassign dynamic typing, that's the word, where I can change the type of something. You can probably also do that in Rust manually. Just like why would you, I guess, is the question. Unless you're making a language, like if you're going to use Rust, you might as well use Rust. But yeah, it's interesting how then you can like opt into those features. And so far Tokyo is the only example of that I've seen. I haven't seen anything else like that happening so far with Rust. Does it exist? I mean, I might do, but I guess it's more just that people who use Rust don't want garbage collection anyway, so I don't know.
For example, you may want to use the Embassy async runtime if you're working with embedded devices. That said,
Why?
99% of the time, you'll use the Tokyo runtime in your Rust applications.
Why?
Let me know in the comments if you'd like a dedicated video explaining how the Tokyo runtime works under the hood. So let's lock in the mental model.
Okay.
Async functions return futures. A future is simply a description of async work to be completed. Unlike many other languages, futures in Rust are lazy, meaning they do absolutely nothing until something executes them. A task is a future that's been handed to an async runtime and scheduled for execution. And a runtime is the engine that pulls those tasks and drives them forward. In Rust, async runtimes are third-party libraries that have to be imported, and the most popular is Tokyo. Okay, so now that we understand what futures, tasks, and a runtime are, let's talk about the next core area that trips up even senior engineers in async Rust: structured concurrency and cancellation.
Okay.
Structured concurrency in async Rust is about deciding how your futures run, and there are 3 common ways to do that: using await to run futures sequentially inside one task, using join to run multiple futures inside one task, or using select to race multiple futures inside one task.
Race.
Let's first look at await. Here we have our initial example of comparing futures in Rust to promises in JavaScript.
Okay.
Now in JavaScript we have the await keyword. It allows us to wait for our code to finish at specific points during execution. Luckily for us, Rust also has the code to finish at specific points during execution. Luckily for us, Rust also has the same await syntax, which allows us to wait for the result of a future. But if you recall from the last section, we showed Tokyo spawn, and now we're showing await. Let's compare these two. We have...
Why is it dot await like that? It's like, it's not even a function call, it's just dot await as a keyword. Yeah, like, it is also interesting how languages build, like async is built into the language. It's like, it's so like a feature from the library that's like added over it. Like it has an async modifier keyword, and like it has like a dot await keyword built into the language. And I believe C++ did the same with like co-await. Zig, I've heard that Zig had a system for it, but then scrapped it in like 2022, and like is still revising it to make it better. So like I'm very curious what they come up with, because it seems like an area that like isn't really talked about enough, given how powerful async is, or just concurrency in general.
Spawn on the left and await on the right. Both seem to be doing something to drive futures forward, but which syntax is correct? They're both correct. Both compile, both run, but there are key differences between the two, which allows great developers to get the most
But spawn is not even built in, whereas await is.
out of their codebase. Let's talk about await and bring in a visual that will help drive our understanding. First, by adding Tokyo main, it creates a thread pool and sets up an async runtime for us.
Thread pool.
Then we make main an async function, which returns a future. The nice part is Tokyo automatically converts the future returned from main into the root task, which is handed off to the async runtime. Inside the main function, fetchUser also returns a future, and will be driven forward by the root task. The root task can start running on any open thread in the thread pool. Here we're showing that it starts running on thread 2, but in practice it can run on any open thread. Second, because we have the await syntax, this means wait for this future to complete while pausing the current task at that point. And that means you're able to use this result later on in your code. Now let's compare this to the that means you're able to use this result later on in your code. Now let's compare this to the Tokyo spawn side for a second. We have
I'm sorry, this example's a bit confusing.
later on in your code. Now let's compare this to the Tokyo spawn side for a second. We have the same initial step as last time. Tokyo main creates a thread pool and the root task starts running immediately. Here the root task starts on thread 1. However, this time the root task hits Tokyo spawn, which creates and schedules an entirely new.
I feel like I'm missing like just context on how multi-threading works in general. I mean, like, I know what a thread is, but like, what's a thread pool? Just a group of threads? Are they managed by some kind of runtime? I don't know. And like, what's the root thread? No, root task. Is that the one that launches threads? It must be.
Task. Noted.
Okay, yeah. So I think the thread pool belongs to the root task, right? And like that pool of threads are the threads that are owned by that task. And the idea is that when that task goes out of scope, I guess, or finishes, then those threads get closed, and they have to all close for that task to finish. That's what I understand.
Notice that fetch user is not run on the root task. It's now being driven by the newly spawned task. Then the spawn task will be placed in a task queue, with potentially many other tasks, and will be scheduled onto any of the open threads. Here, thread 2 is chosen to run the Tokyo spawn task. But what happens at step 5? We don't have any await syntax to signal we plan to use the result. By only spawning a task and not awaiting it, the task is only scheduled and run, but we don't actually wait for the result. It may succeed, it may fail silently, but nothing comes back to us to actually use later on in our code. This is known as fire and forget. Although we're showing fetch user in order to remain true to our original example, we're going to update our code and add one of the most common cases for fire and forget: logging. Notice that this is the same exact structure we have with fetch user. It's only showing a slightly different use case. A best effort approach is taken to log in the background, but we don't explicitly need to wait for anything to be returned to us. We're okay if the log attempt succeeds or fails silently. So let's do a quick recap.
I mean, we're okay in the sense that it's not, like, nothing's dependent on it, but maybe we still want to see the log though, you know? So I don't really understand that.
Of what we just talked about. We learned that although we can use fire and forget.
I feel like I'm watching the wrong video here. Really, I should be watching a video on like concurrency in general.
On fetch user, it really benefits from using await, because we care about using the result later in our code. And as we've seen, we have the ability to spawn a completely new task using Tokyo spawn, which is great for scenarios like fire and forget. So far, both await and spawn solve a core problem of being able to drive futures forward on the async runtime in Rust. But currently, we are only working on individual async functions, which return futures. But what if we want to run multiple futures at the same time inside one task?
I mean, is that the point? Like, I don't get why print line here is an async function. Like, how does it work? Like, surely the whole point of this is that you run multiple things at once, right? So it's like, while I wait for this, do this instead, you know, type thing. But like, unless like I'm thinking about it wrong or something. Like when I do async await in, let's say, my Unity game, and I load everything before the start of the game. Like maybe I load my resources asynchronously, but ultimately I need to wait for them all to load before I can then proceed to the next step, right? So then, like, that's where I have a loading screen, God forbid, and right. Like I still have to use the result. Yes, like what's the actual benefit then of using async await even? Because I'm familiar with multi-threading for multi-threading, but not so much for async await. Yeah. Okay. I think I need a more general introduction to async await.
There are useful macros Tokyo has that can help in these scenarios. Let's assume you want to run multiple
macros,
independent futures at the same time inside the same task.
by design.
This is where the join macro comes in. If you're coming from JavaScript, you can think of join like promise.all. In Rust, the join macro is the wait for everything tool. You can give it multiple futures, and it drives them forward concurrently until all of them complete. This is great when you need multiple results before moving on. If we expand our fetch user example, imagine we need to load a config file and connect to a database before fetching the user.
But like why, cause like threads yield, right? They yield while they wait for something to happen. That's like kind of how like operating systems also work. But then like, why would I need to do that for something like this? Like, is it because like loading the config has multiple steps where the thread may want to yield and then have another thread do its thing, right? Because like ultimately that saves time, because like rather than like wait for one function to just wait and waste time, like it actually checks. But like, do you even need to like have threads for that? Like, I know threads are like a CPU thing, but can't you code that manually as, I mean, sorry, an OS thing. But can't you even code that manually, where like you have like an update loop, and then, you know, it just checks with the flags, like, has, like, is, I don't know, is content ready, and then if it's not ready, then do this other thing, and then do whatever. I mean, I'm guessing you could code it manually, otherwise, how would they be coded, right? But, I don't know. The question is, when would I use async await and why? Like, even in C#, I had to use it to load certain resources, but I didn't fully understand the why, and that probably also made it hard for me to structure my program properly.
Neither the config or the connection to the database depend on each other. You need both. So it makes sense to do both at once, and this is exactly what join is for. If we look at a visual, we can see that two futures are...
I mean, like, if the threads are running, like, on two different CPU cores, fair enough, right? Like, that's true concurrency. But if it's just switching back and forth, I wonder how that's handled.
...are inside the same root task, and then run on a thread. The join macro pulls both futures concurrently, until they both complete. Both connect to DB and load config are returned. Now, you might be wondering, this Tokyo join syntax looks great, but is there really a difference between just running both of these futures using the await syntax we've seen? Yes, they are very different. This commonly trips up even senior developers new to Rust. Although both look to simply be running futures on the root task, it's how it's happening which is critical to understand. Let's assume that both load config and connect to DB would take 1 full second to run by themselves. On the left-hand side, Tokyo join uses what's called interleaving. It runs both futures concurrently, allowing the runtime to switch back and forth until both are done. This comes with a minimal overhead. For simplicity, back and forth until both. It runs both futures concurrently, allowing the runtime to switch back and forth until both are done.
Right. Well, like, my question is, what triggers the back and forth?
This comes with a minimal overhead.
Like yielding, I guess, right? Okay.
For simplicity, we're showing that the overhead took us an additional 100 milliseconds for that context switching.
Right, but then I'm guessing the other one waits and then does the other one awaits, right? I guess that's how it works then, right? Like if I have an async main, rather than freezing the thread, like let's say I did load config and it took 5 seconds, right, to process its result. If I did that without async, then that would just freeze the application basically for 5 seconds, and like the user would see the thing just freeze and be like, what's going on? Whereas if I do await, then it will still run, but then when it finishes, it will proceed with the next instruction. But like, what's running? Like I assume for like an async main function, it's the same thing. Like nothing really happens, right? Or is it like it only freezes when it reaches a point where it needs the result of config and db, like from here? Yeah, I don't know. I really benefit from just knowing how this works by probably using it. Like I see how it's good for like loops, you know, like if I have like an application loop and I want to say, you know, await this and then like hold off from this until that happens, and then in the meantime just like let the user do other things, right? Like that makes sense. But otherwise, like this example is confusing to me. Like, this video, yeah, seems to assume you already have knowledge on async without Rust.
But this isn't fixed. Let's compare
Fair
this
enough.
to the await example. The await syntax causes us to completely wait for load config to finish before connect to db can finish.
Okay.
Here we have no
Yeah.
interleaving. We must wait the full one.
That's weird, because like then it's effectively the same as if you did it without async. So it's just a weird example to highlight.
1 second for each future to finish. This difference can be monumental in a production codebase where end users demand the lowest latency possible.
Yeah.
So using the join macro is a clear winner in this scenario. Now let's discuss a...
What I don't like is that you need to use Tokyo. Like, I know Rust in general doesn't put too much into its standard library, right? But like, there's something nice about not having to use loads of dependencies, because the standard library already has them implemented, you know? Like, I know Tokyo is like just one runtime, but like surely there's like a way to emulate this, but just with normal Rust.
different scenario. What happens if we don't necessarily care about both futures finishing? Imagine you want to run multiple futures concurrently, and you only care about the first future that finishes. Basically, what if we want to get the
Race.
fastest future to the finish line? This is where the select macro comes in. Again, we have a nice JavaScript parallel, which is promise.race. In Rust, select is the race tool. You
Okay.
give it multiple futures, and whichever one completes first wins. We've updated our example such that we've already loaded our config and db. But this time we want to race our fetch user against a 5-second timeout.
Okay.
We do so because in a production setting, we don't want to wait indefinitely on a slow or hung operation.
That's a cool example, yeah. That's cool, yeah. Cause like the way that I would do this, you know, what's the word? What's the word for like doing something like unknowingly? I forgot what it was, but like the way that I would do this without concurrency, like without threading, would be to literally just like start a timer and say like do this, and then like each loop of the fetch user, I would say if timer has reached 5, then return false cannot query, right? But yeah, this makes it easier because it means the fetch user can be a completely separate thing, and then you can determine it separately and just say, yep, race these two threads. Let's say I do duration from seconds, right, with 5, and then if that happens first, then just use that. Or, you know, maybe I want to fetch user or fetch something else, and then if that fetches first, then fetch that instead. So yeah, that makes sense. Like, as I watch this video, I was trying to think of like ways that I can use concurrency in my projects. Maybe. I guess because I haven't done much network stuff. Like, most of my projects have been very like low level, like modding, game development. Yeah, so like I haven't really used systems where I would benefit, not benefit, but like I even use systems where I need to wait for something. Now at some point in my game development, I would probably need to have that to like load resources from disk and stuff like that. But generally speaking, they're quite fast anyway. So I've reached a point where like there's like a bottleneck. Plus my games are like in extremely early stages of development. So I'm not even on like a file loading system yet. I just load files as I need them. And like in modding as well, like yeah, like I can definitely use concurrency, like multi-core concurrency. But like as far as like threading goes, like this, with asynchronous code, not so much, because like it is quite sequential to do things, and like I'm not like waiting for like an API to get back to me. Whereas if I do like web development, then that's different, because then I do need to wait for a server to get back to me, right? And like I don't do any like multiplayer stuff either, by the way. So like I've done 0 server side projects. I've like the most I've done is Leptos, and that's completely wrapped for me, but in Leptos, so I haven't really looked into that. Yeah, but like I'm trying to think like maybe I should make a web app of some kind in Rust without using Leptos, just to like kind of see. I mean, not a web app, but like try to make like some kind of like server side, like some like some app that accesses an API, and then do something with it, like some kind of like web scraper maybe. I mean, it's a very useful project to make. Like, let's say I want to make a web scraper to look for jobs, right? I should probably do that. That'd be a pretty good example of something to do that could make me learn how to use async. So there you go. There's an idea. And like aside of servers, I'm thinking like OS, like things like, again, like loading files. That's it really, isn't it? Yeah. It's mostly like server side things that you want. Or things that just happen to take a long time on your system. Like, I don't know. Like, let's say I'm converting a video game format to JSON, so I can edit it more easily, right? That'll probably take like a few seconds, maybe. So I could run that asynchronously while I do something else. But like, what else am I doing at the same time? I don't know. Would like a loading like a progress bar? Would that use asynchronous code maybe? Like every time it finishes with some step, it yields back to the main thread, and the main thread updates the progress bar and then goes back into the other thing. Could do that, right? That's an idea. Like, I'm just thinking of things I could do to test this out, whether it be in C++ or Rust.
Let's bring in the visual to aid in our understanding. We can see that this is very similar to our join visual, but this time we can see that at step 2, the select macro polls multiple futures and whoever completes first wins. For example, if fetch user finishes first, it would win, and the timeout
Yeah, this is a very cool use case, actually.
branch would lose. Now there's one extra piece that catches developers off guard. When the timeout branch loses, the future is cancelled immediately. It doesn't progress forward or run to completion. This is the idea of cancellation, and it's different from other languages like Go. In Go, developers have to explicitly cancel Go routines. In Go, we must explicitly tell losing Go routines to stop so they can exit early instead of doing unnecessary work. But in Rust, you don't have to cancel losing futures yourself. The cancellation is implicit. Once
it's implicit, but keep in mind this is using the Tokyo select macro. So like, yes, like it's in Rust, but really like it's in Rust using this library that gives you a macro that does stuff in the background for you. Which isn't really accurate to saying it's like in Rust.
Once one future wins, the others are automatically dropped, meaning Rust immediately stops them and cleans up their state. The benefit is this makes cancellation predictable and zero cost, because Rust can clean up resources immediately, and most of the time, that's perfectly fine. But what happens if you're racing futures and you end up in the middle of a multi-step operation like a transaction? Yeah. This is where a common footgun in Rust occurs, and it has to do with something called cancellation safety. Imagine you're writing a protocol message to a TCP stream, but you're doing it inside of a select macro. The send message future starts being pulled. The header gets written, but then you hit the 5-second timeout. It saw the beginning, but it never got the rust, and your protocol state is now corrupted. This is what the Rust community means by enforcing cancellation safety. A future is cancellation safe if dropping it midway does not leave your program or external state in a broken or partial condition. Because with select, you are not just choosing the fastest branch. You are also choosing to cancel the losers. So the question becomes, if select or a timeout can cancel a future in the middle of a write, what do we do instead?
Well,
the idiomatic fix is not to pretend the write can safely resume. It usually can't. Once the timeout fires, the state of that connection is now questionable. So on the left, we still have our send message and we race that against sleep. If send message finishes in time, great, the message was fully sent. But if the timeout branch wins, we do something very important. We shut down the stream immediately. We are not making the write itself magically cancellation safe. The write can still be interrupted halfway through. What makes this pattern safe is that we refuse to keep using the connection afterward, and that's what gives us cancellation safety. With that in mind, let's review all that we've covered in this section regarding spawn, await, join, select, and common footguns. Here are the rules of thumb. Use Tokyo spawn if you need a completely different task to be created. Use await if you need to wait for a result to be returned. Use join if you have independent futures that can run concurrently. Use select if you plan to...
Does concurrently ever spawn different cores? Like, is it just automatic? Or do you have to do it explicitly somewhere?
race futures
I'm aware
against...
that it's Tokyo, but I mean, like, if I weren't using Tokyo and I were to implement Tokyo, does it have some way to access cores, or is that just something? Is that something that the CPU decides itself, if it can determine if things can be running, like literally, in parallel?
each other. And in the context of the select macro, cancellation simply means the losing futures are automatically dropped. You don't need to explicitly call a cancel method. This works well for things like timers or reads, but it becomes dangerous for operations like writes, where the work can be interrupted halfway through, like we saw in our select example. If you understand these common ways of deciding how futures should be run, you understand some of the biggest differences between async Rust and async code in other languages. Now that we've covered structured concurrency and some of the major async footguns, the other very important piece we need to understand is sync and async interop. By the way, these are exactly the kinds of async Rust concepts that we tackle in depth inside the Rust Live Accelerator. The next cohort opens this June. More details at the end. This is exactly what it sounds like, mixing asynchronous code with synchronous code. And this is one of the easiest ways for production async systems to accidentally slow down or stall entirely. Let's set the stage with a common scenario a high-frequency options trader would face. You need to fetch a large amount of data from a high-frequency data provider like Data Bento. First, you add Tokyo main, and an async main function like we've seen in the previous sections. Then we make a call to fetch options and calc Greeks for 3 different tickers. This makes calls to fetch option quotes to get the data, and then a call to calc Greeks, which does a heavy CPU computation to calculate the implied volatility. But notice we're calling a wait on the futures which runs them sequentially. We don't want to do that. Instead, let's bring in one of the macros we learned about, join, which we know can process many futures at once inside one task and gives us a large speedup over sequential waits due to interleaving. In our case, it helps us with the ability to fetch 3 different API requests at once. So the I/O piece of this code is now sped up, but we are still calling calc Greeks, which does CPU heavy work. At some point, one of our futures will hit this large CPU computation and hog the async runtime from moving forward. Let's picture this. We have our root task, which is driving futures A, B, and C to completion. The root task moves onto worker thread 1.
Like, is this where the whole, like, it's infectious comes in, right? Like, you want calc Greeks to then also be async and yield when it can, right?
And starts executing. But eventually, those futures hit calc Greeks, a heavy CPU computation. And here's the problem. This work doesn't yield. It doesn't hit a wait. It just keeps the CPU busy until it finishes.
Could you have a system, or like a language where all functions were async? Everything is async, you know, by default. All you do is specify which parts cannot be interrupted. So then everything can run asynchronously until it hits a point where you need to force, rather than specifying where things are async, have async be the default and specify where things are synchronous. Can I do that instead? Like, would that work? I mean, like, that's like the naive, that's the word. That's my naive thought right now. You know, in the same way that Rust makes const a default, can I make async a default instead? Since async is so infectious. I mean, like, infectious, like, not like in like an evil way, but like in like, if I want to use async in my project, I kind of want everything else to also be async compatible.
So the root task gets stuck on thread 1 the entire time. That means the runtime can't schedule other tasks on thread 1 while the CPU computation is running. So what do? We need a way to run the CPU heavy work without blocking the async runtime. And that's exactly what Tokyo spawn blocking does. It lets us move that computation onto a separate thread pool designed specifically for CPU bound work. In other words, blocking work. Now let's walk through what happens. Step 1. The root task starts on the non-blocking thread pool, the same one we've been using throughout the video. This pool is optimized for async work that can pause and yield. Step 2. When we hit calc Greeks, we call spawn blocking. This offloads the CPU heavy work to a separate thread pool for blocking work. And here's the key detail. The root task doesn't just sit there waiting, it actually comes off the thread entirely. That frees up the runtime to immediately run other async tasks. Meanwhile, the blocking work runs independently on the blocking pool. Step 3. Once the work finishes, the root task resumes.
But how? Is it on a different CPU core? Or does the CPU instructions just like switch back and forth? Like, what does the pool impose on the threads such that having a different pool means that I can, like, does each CPU core have a thread pool? What is a thread pool? So it's like a makeshift. No. It pre-creates threads, and then assigns them as they're ready, rather than spawning a new thread individually, right? So it's kind of like. It's kind of like creating an array of a fixed size that you know will be the limit, rather than creating a vector that will grow and reallocate. It's kind of like that. Like, you save the time by just making the threads first, and then assigning to the threads, rather than making the threads as you need them. Right? So, like, what's that got to do with having, like, different thread pools? Why have multiple thread pools? CPU bound versus IO bound, yeah. What? Claude. How do you have it work? Why does that from one pool to another, from pool A to B, free up A to do stuff, while B also does stuff. Right? Like, yeah, I don't know. Get to that. Come back to that.
And it doesn't have to resume on the same thread. It can continue on any available thread in the non-blocking pool. So the mental model is start on the async non-blocking pool. Offload CPU heavy work to the blocking pool. Let the task step off the thread while the work runs. Then resume later on any available thread. That separation is what allows Tokyo to handle large amounts of async work efficiently, without letting one CPU heavy task stall the entire runtime. So far, we've covered the 3 areas of Async Rust that trip up even senior engineers. But an understanding of these topics isn't enough. You need to apply these to real-world production scenarios, which is why we created the Rust Live Accelerator.
Yeah. Spawn blocking is a separate thread pool for I/O bound blocking code, not CPU bound. For CPU bound work, you should use a separate thread pool like Rayon. Rayon? I've heard of Rayon, but like for I/O bound blocking code, not CPU. I mean, that's what we kind of saw in the summary, right? I/O bound, not CPU bound. Right. Same task corrupted in a single thread, which is on a single thread. Right? In Scala, a task is usually lazy while future is eager. Okay, whatever. The Go example is wrong. Okay, sure, whatever. Right. Let me save this and watch later. Okay. Let's have a look. A thread pool is a fixed set of working threads pulling tasks of a shared queue. If all workers in a pool A are busy running long CPU-bound tasks, and any new task message to A just sits in the queue, even quick unlimited tasks, because no thread is free to pick it up. By moving the CPU-intensive task to pool B, pool A's workers are no longer blocked by it, so they're free to immediately pick up other queued work. Meanwhile, pool B's threads handle the heavy task independently. The OS scheduler transmits actual CPU cores. Okay, cores, yeah. Okay, so does this only work in multi-core then? No, okay. Single core. The OS still transmits between all threads, so A's threads do get scheduled periodically even while B's task runs. They're not starved, just slower, since every thread is competing for the same one core. So you still have concurrency, but just not parallelism. Multi-core, it's different, okay. Right, so the OS still transmits between all threads, so A's threads do get scheduled periodically. Right. But why can't the OS do time slicing with one pool? Is a thread pool even a real group of threads, or a simulated one? By the way, thinking in terms of Rust. Okay. The OS does time slice other like OS threads, regardless of which pool they belong to, but a thread pool worker doesn't time slice between queue tasks. It pulls one task off the queue and runs it to completion, then pulls the next. Okay, so like that's the model then. So if pool A has 4 worker threads and all 4 are stuck running long CPU tasks, a 5th quick task just sits in the queue with no threads to grab it. Okay, but then like, if I have 4 pools and only 4 tasks, then it's fine, right? Right? Like the video made it sound like if I have one that blocks a thread, like just one thread, then that completely blocks everything. It didn't say that it only happens if the threads are full. Weird, man. I really hope that video didn't like give me a bad impression of like a bad idea, because that's gonna be annoying to unlearn. The OS comprehensively stop it because it's not scheduled to enter any thread yet. So like this just sounds like creating more threads. Full stop. Okay. So basic way on thread pool, real OS threads spawned once and reused, each blocking pulling tasks from a shared queue. Okay, Tokyo. Yeah, but tasks, features, are lightweight. Many tasks can multiply cooperatively. Right. I watched this video explaining async Rust, and it gave an example of, I don't know, calling 4 async functions that had long sync code, that had long synchronous code, that each called the same CPU intensive non-async function. He then used this as an example for why you would want to move, call, what's it like spawn something? Let me actually just be accurate here.
Isn't enough. You need to apply these to real-world production scenarios, which is
spawn blocking. Tokyo task spawn blocking. Blocking on the CPU intensive function to use a different pool. But that sounds like the CPU intensive function blocks the entire pool. But what you're saying is that this is only a concern if the pool happens to run out of available threads. E.g., I have 4 of these async functions, but only 3 threads in my pool. Poolo. Or is one blocking just something else? Because, like, again, it's CPU versus CPU bound versus IO bound. I've heard of that. But, like, how do you target that? Okay, what you said, for blocking tasks, fewer worker threads and tasks. So some tasks just wait. Yeah. The non-preemptible problem. A blocking call inside an async task never yields, yeah? No matter how many threads you have, so even with 4 threads or 4 tasks, none of those threads can do anything else with each blocking call finishes. Now here's you find in a toy example where there's 4 tasks and anything happening, but in real Tokyo app, those same worker threads are expected to service other unwanted tasks spawned elsewhere, the IO reactor timers, etc., yeah. That only works if tasks yield frequently, yeah. A blocking call breaks that assumption for whichever thread it lands on. Okay. But I don't understand how moving the task to another pool magically makes it async compatible. Does it not still block? Yeah, on a single core processor, does it not still block all the other threads? And by it I mean, does the CPU intensive task not block all of the threads? Okay, so probably doesn't transform the function, it's still a normal blocking call. What it does is hand it off to a separate real OS thread pool that exists specifically to absorb blocking work. The async worker threads never touch it. On a single core, why does it block everything? Yeah. The async worker thread runs tasks cooperatively, so it only gets a chance to switch to a different task when the current running task hits in a wait and voluntary yields. A blocking call never yields. So yeah, so it was running on an async worker thread, that thread is stuck, yeah. No amount of OS time slicing helps, because from Tokyo's perspective, there's nothing to switch to within that thread's task that Tokyo returns. OS threads themselves, however, are preempted by the OS scheduler regardless of pool. Even one core will forcibly interrupt a blocking pool thread periodically and run something else. Okay. So is the CPU only able to block per pool rather than per threads? Like, I don't understand. No, flip that. The OS operates strictly per thread, never per pool. Yeah, it's not a concept on the OS, but it's purely an application level grouping of threads that Tokyo maintains, yeah, for its own bookkeeping, okay? Only the one thread actually running the blocking call is occupied by it. So it helps, not because it changes what the OS does, but because it moves the blocking work off a thread that was overloaded with responsibility. So in this scenario, pool A, or like thread pool A, was in fact on one CPU thread. No. Dude, what the fuck? Pool A normally has multiple threads. By default, Tokyo spawns one per CPU core. Yeah. One per CPU core. One per CPU cores, okay? So on a typical multi-core machine pool, A might be 8 threads, not 1. What I'm describing, a blocking call was still on the thread, and everything in the thread juggling happens per thread within that pool. If you block on a thread 3 of pool A's 8 threads, tasks that were scheduled on threads 1, 2, 4 to 8 keep running completely unaffected. Yeah. This is a degenerate case. A happens to be exactly one thread, which is why blocking felt like it stalled everything. Yeah, so on a single core, is my thread pool A only one thread? Only one OS level thread? That's what I'm asking. Why are there no straight answers, bro? Give me yes or no, on God. Not inherently. By default, yes. Tokyo's default working count, number of logical cores, so on a genuine okay. That's a default heuristic, not a hard rule that you can override it. Okay. So is the reason the video I watched gives the example it does because of how, because of the assumption that each thread pool was only one OS level thread. I mean, obviously, as you assume something about the video. That's not the actual reason. It's worth correcting because real issue is orthogonal to thread count. The very sample works even with a normal multi-core pool, 4 or 8 async threads. Because the problem was never only one thread exists, it's each async thread delivers many tasks, not just one. Even on 8 threads, if you spawn 100 lightweight async tasks, Tokyo work steals and multiplexes them across the 8 threads. Block one of those threads with a CPU heavy call and every task that would be scheduled on that thread stalls. Yeah, but then how does moving it to a different pool fix the problem? I don't understand. These 4 tasks all end up funneled through a small fixed pool of async threads, and blocking calls don't yield. Okay. I feel like I'm getting really non-straightforward answers here. Can you just break down what's the why the example in the video requires using a second pool, and what would happen otherwise, and why? The example: 4 async functions, each calling the same CPU heavy blocker function, default Tokyo runtime, save 4 worker threads, 1 per core. So 4 threads per core, okay? Without spawn blocking. Each of the 4 blocking calls gets scheduled onto one of the A's 4 worker threads, yeah. A blocking call never yields, no wait inside it, so once the thread picks up, that thread is unlocked, that's fine. All 4 of 8 threads get taken hostage simultaneously, any other task needs to run, has nowhere to go. Okay, so imagine we have these 4, but also in the background there's other ones, and those get stuck. Fair enough. With spawn blocking, the 4 calls run on B's threads instead. Okay, B is a large pool, up to 500... Why is B a larger pool? First of all, built for exactly this. Is it because of spawn blocking? Pool A's 4 threads are never touched. They stay free to keep running the async event loop. So, okay, so is it that the thread pool that spawn blocking uses is specifically designed, or is specifically intended for CPU tasks, for expensive CPU tasks? Almost. It's intended for blocking calls generally, not specific CPU expensive ones. Okay. So can I say then that pool A is smaller than pool B, generally speaking? Because the way I was thinking about it was that I have pool A and pool B. Pool A and pool B are like the same. Like, their sizes are the same. But here, it sounds more like B is a special thread. So is pool B a special pool that differs from other normal pools, like pool A? Yes. Okay, that makes more sense. So pool A and pool B are not just generic pools. Pool A is specifically our async worker pool that we want to have free to do async tasks and switch between different things, fast. So because of that, we don't need as many threads. Pool B is the blocking pool, which is specifically designed to be able to take those. I mean, not necessarily expensive, but to take CPU tasks in general that would otherwise block the async worker pool, right? The threads in that async worker pool. And that's why it is more. So here it says small, usually equal to the number of cores, whereas pool B is elastic, it does spawn threads on demand, okay, and there's a cap of 512. That makes more sense. Right, that was missing from the video, I feel. Okay, that makes more sense. And then also, this is a different chat. I'm curious. Could there be a language that has all that, rather than opting into async by marking functions async, all functions were instead asynchronous by default. I mean, this is my naive take, because it sounds pretty simple. Okay, not many languages make functions explicitly async by default with no sync escape hatch, because that creates the same function coloring problem in reverse. Bob Nystrom, the name's somewhat familiar. What color is your function? Now your sync code is infected by async instead of the other way around. Green threads. Oh, so they're called green threads. Every function call looks synchronous. Under the hood, if a goroutine blocks on I/O, the runtime scheduler parks it and runs another goroutine on the OS thread. You never write async awaits anywhere. The concurrency is invisible at the call site level. Invisible. Okay, Erlang. Look, I never used Go. I probably never will. But all I know about Go is that it's designed to be very easy to use and very quick to use. The reason I probably never use it is because of the recent changes to it have led to people who usually champion it to not want to use it anymore. Otherwise, I probably would have at some point. Erlang, same idea. Haskell. I'm not to that. So the design space actually got explored, and the industry answer wasn't to make everything async. It was make blocking look synchronous. But does this work in systems level languages like Rust, Zig, and C++? That's my main concern, because I only care. Not really. Yeah. So they tried them and they removed them. Okay. Where's FFI? Okay. So what if a systems level language instead went for the everything is async approach? Because the way I see it, an async function can be made synchronous if you chain a bunch of awaits, like task A, or so await task A, await task B, await task C, right? These are not run concurrently because they come one after the other. I mean, not made synchronous, but the behavior can come from it. Let's see. Okay, compilation cost or semantics. It's expensive. If every function can suspend, the compiler has two options. Every async function compiles to a heap allocated state machine. Every async function compiles to a heap allocated state machine. If every function worked this way, then even this would need this treatment unless the compiler could prove it never suspends. That kills inlining. Okay. Suspend by switching stacks instead of transforming into state machine. This is actually what you're describing and it already exists. It's what Go and Erlang's green threads are. Right, yeah. Because Go has everything be implicitly waitable, right? Just call Go in it. But there are costs. So your proposal doesn't dodge the trade-off, it rederives it. Zig's original async design, pre-2022, before it got pulled, functions were not marked async. The compiler inferred via calling analysis what their function could suspend. then automatically sized its coroutine frame and promoted callers. See, that's interesting. That's colorless async by compiler inference, but not by making everything a green thread. It got pulled because frame size inference broke down around recursion, function pointers, and generics. The compiler couldn't always know. Okay, so like the issue is the compiler, I guess. Like it's like in terms of what it can prove. WebAssembly stack switching. Okay, so it's an optimization problem. Modern compilers simply lack the ability to prove when things are synchronous or not. But then what if users could explicitly mark a function or a block as sync? Holy typo. I realize there are limitations to Async Claude, but partly because I'm not the compilers are good enough yet. The core issue, knowing what the function can suspend requires knowing everything it calls transitively. Yeah, few function pointers, trait objects, vtables, and recursion. It's undecidable. Right. It's cool that Zig tried it. If you mark a function sync, the compiler must guarantee nothing it calls can suspend, which is just to walk that function's entire call graph and verify that them are. Right, so like, for this to work, the compiler would just have to trust you, right? If you mark a block, same deal. Prove nothing so the scope can suspend. Right. Okay, functions declare the effects they may perform, including may suspend, and the type system tracks and checks it structurally rather than requiring a source of call graph for inference. Right, so could effect-based programming do this instead? And because they're very different. Okay, because like I've heard about function not coloring effect systems for a while now, or like effect programming, or like effectful programming, whatever it's called, and I haven't really been too. I don't know. I haven't seen the appeal so far, but if it can help the compiler determine how things work, right, without having to like guess, basically, or not guess, but like infer it itself, then that's pretty useful, right? Like can block, can mutate, right? Like rather than checking does this mutate, you know, through like a call graph, it can just check the structure, because if I say it's like I assume the way it works is that when you first put the effect on the function and say this can mutate, this can block, right? The compiler just has to check that one function, right? And just say, okay, can it, I said that this can block, or so like does it have any blocking? Oh no, actually rather it checks, does this have? No. Okay, what it can do is go through each function, right, and check what's happening here. Oh, okay, look, it's blocking. Does this function have can block in the signature? If it doesn't, then throw an error and say, you need to add this effect, right? And say, or like specify this effect. What that does is that when another function needs to check that function, rather than doing the whole the same thing again and saying, okay, check each one, is it blocking here, is it blocking here, it doesn't have to do that. It can just look at the signature and see, okay, there's this effect here as specified by the user. So I assume that So I assume that the user already checked that it can, or like maybe they got a compiler error. I don't care. All I see is that it can throw. It can block. Therefore, I'm going to say it can block. Right. That is cool. That is actually really cool. Okay. So tell you what. The next step is look at verse, because verse is potentially the very first programming language, mainstream programming language, to have an effect system. I know what Ocaml does, apparently, and I know like Kojo does and whatnot, but like those are like research languages. Verse is a language that's going to be used by Unreal Engine developers. So the fact that it has an effect system definitely makes it worth checking out. So I think that's what I'm going to do next. I want to check out verse, and I want to check out the effect system. because before this, I did not understand why you need an effect system. This is giving me some idea now of why you might need it. So let's do that. So to finish off, let me go to Discord and just write a few notes even on this. I did some research into async programming. From what I understand, effects, and I think I finally have some understanding of how effects like Kojo are useful, because it allows a compiler to check things like can block, or like blocks, you know, like thread blocks, right? Easily, without having to prove it each time it needs to check a call graph. That's what I understand so far. I'm gonna have a look at verse next to really see effects in action. It's interesting because verse because verse may just be the first mainstream programming language to use effects, and it's used in game development, no less, which is a field where performance is very important. So, okay, cool. Okay, good. Feels like things are coming together. So, yeah, verse. Head west, head to verse. That's what I want to do. Yeah, why is this so like... Okay, right, so verse. I'm gonna look at verse, and I still need to finish a Swift tutorial, actually. I haven't finished a Swift one. That's like a whole other thing. Like Swift I want to look at from like a software architecture perspective, but verse will be interesting from a programming language design perspective. This whole effect system could be very interesting, and I'm also aware that verse doesn't have user-defined effects, right? But I wonder if that matters. Like, just in general, like there's a lot of things that you don't need to have be user-defined, or like allowed to be user-defined, if the language just has them, like just covers all the useful things, right? Like I feel the same way about like attributes. Like for example, you wouldn't need like an endianness attribute if the language just had little endian and big endian built into the language for when I use like a binary type, right? But then the useful thing about attributes is that it lets users define things that you do not have the foresight to include. So we'll see as well like which effects did verse specifically choose to pick out for the benefit of its language. I'm very curious about that. So there you go. And also I might also check out what is Zig doing now. I wonder if Zig might even move to an effect system, because it just sounds like to me like it's just like an effect system just makes it easier for a compiler. Sorry, not easier, decidable for a compiler to determine certain aspects of function calls, right? Which, yeah, like why wouldn't you use that then? Because at that point it's just an ergonomics thing. So again, verse is meant to be used by Unreal Engine developers, people who may not even necessarily be like the most competent programmers. You know, they're sunsetting the blueprints, right? So I assume that they want to make it ergonomic. So this would be very interesting to look at. Yeah.